Hi and welcome everyone again. This lecture we're going to go over matrix spaces and the rank of a matrix. So let's start with the definition of matrix spaces. If we have an n by n matrix, so let's see what the row space is. The row space of A is the span of the rows of A. The column space of A is the span of the columns of A. And these are just the components of vectors. And the null space of A is the set of all solutions of AX equals to 0. And we know that's the homogeneous system. So, and I did put the summary here for you. The way you can write it again, our matrix is m by n. The row space of A is the span of the rows, and this is in Rn, so remember that. The column space of A is the span of the columns, so then rows and columns, these are vectors again, and this is in Rm, and the null space of A is X's are in Rn, and is the solution of the homogeneous system, and I will show you with some examples. So one little notation here, the column space, I do call it the call space because it's just easier and shorter, and you can do that too. Now, if we have an n by n matrix, then we can have its transpose, which is n by n, and we switch the rows and the columns. So the null space of A transpose, these are y's, I call them y's in this case, of, they are in Rm, and it's the solution of AT, they transpose times y equals to 0, which is again a homogeneous system. I will show you an example. The row space of A is the same thing as the call space of A transpose, that's in Rn. The call space of A is the same thing as the row space of A transpose, and that's in Rm. Again, we're always talking about m by n matrix. And the null space of A is in Rn, and the null space of A transpose is in Rm. Let's see a little example here. So here we have a 2 by 3 matrix, and I put the rows, again, these are vectors, and I put you can see the columns, I call them C1, C2, C3, and the row space of A is the span of R1 and R2. And if I write that, the span of 1, 2, 3, that's the first row, and that's the second row. And as you notice, this is in R3, so which is n in this case. The call space of A is the span of the columns, the column vectors C1, C2, C3, and if you write this, the span of 1, 2, 2, 4, and 0, 5, and again 1, 2, 2, 4, and 0, 5, and that's in R2 right here. To find the null space of A, you have to solve the homogeneous system. So I did write it here. So you can, that means you can take your matrix times x1, x2, x3, and you put 0 here. And again, if you want to do this fast, you can just write the matrix and then find the RREF of that matrix by doing some row operations, and that's what you get. And you can say x plus from here, x1 plus 2x2 is 0, and if I put that here for you, this is your x1 and that's your x2, and that's your x3. Let's x2 equals to t, and x3 equals to 0. So you rewrite the system. Here we have one free variable, which is this non-pivot column, and that's x2. You can call x2 to be t, and from here you can say x1 is negative 2t, and obviously you can see that x3 equals to 0. So if you write x1, x2, x3, negative 2t, t, and 0, you can factor out t. So you get negative 2, 1, and 0. So the null space of A is the span of that vector. That's a basis for the null space. And this is in R3, which is our n in this case. So, and I put negative 2, 1, 0 as a basis for the null space of A. Now let's go do some more detailed work. Here we just, for this matrix, found a basis for the null space. Let's see how we can find basis for the row space and the column space. Please pay attention to that. To find the basis for the row space, one thing you need to know, the elementary row operations do not change the row space of a matrix. Thus, if B is obtained from A using an elementary row operation, then the row space of A is the same as the row space of B. So if R is the RREF of A, then the non-zero rows of R form a basis for the row space of A. I will show you an example. So just know, if you want to find the row space or the column space, you need to find the RREF of the matrix, of the original matrix. Now let's check for the column space. If an n by n matrix A has reduced row echelon form, that's the RREF, and again, from the last lectures also, we're going to always call the RREF R. Then the columns of A that correspond to the leading columns of R form a basis for the column space of A. And I will show an example. Once you see the example, then that will be very clear. Basis for the null space. So we already did that, but the null space of A is the same as the null space of its RREF. And again, I called R to be RREF of A to remind you all the time. This is very important. If R has k free variables, so you check the free variables, then the null space of A will be k dimensional. So which is the nullity. So if you want to find the nullity or the dimension of the null space, you can just count the number of the free variables, and that's going to be your number. Let's go over this example. It's a pretty big matrix. So if we notice, well, this matrix, what we have is 6 columns and 4 rows. So this is 4 by 6. And the RREF, I already calculated, or it will be given to you for those big matrices, or you can use technology to find it. So this is also 4 by 6. Now, the question is, find the basis for the row space of A, the call space of A, and the null space of A. So we're going to see how RREF is going to help us to find those. So the row space of A, what you need to do is to go to the RREF and then get the rows with the leading ones. So it's that, and the non-zero ones, of course, that and that, and these are your leading ones. So these are going to be a basis for the row space. And if you write those, so we have 1, 0, 3, 8, 0, 5, which is the first row of the RREF. Then we have the second row of RREF, which is right here, and of course the third row of RREF, which is right there. And notice this is in R6. So that's the row space. Now the call space of A is going to be the span of 5, 3, 1, 2, and so on. Let's read those. So we go to our pivot columns. That's a pivot column, and you take the corresponding column, which is 5, 3, 1, 2. So that's 5, 3, 1, 2. Then you go to the second pivot column. So that's a pivot column, and you take the corresponding column in the original matrix, which is 7, 4, 2, 4. The next one is 5x, the fifth column. So that's a pivot column, and you take the corresponding column in the original matrix, and that's 6, 3, 3, 5. And we have it. And notice that this is in R2. So the call space of A is the span of these three vectors, and they are linearly independent. So the null space of A, you have to solve again the system AX equals to 0. Let's go see what we have here. Directly from RREF, you can go ahead and solve that. First of all three variables are x6 because it's not a pivot column, x4 because it's not a pivot column again, and x3. And the other ones are just the basic variables, x2, x1, x2, and x4. So you can just rewrite the system. From the first line, we have x1 plus 3x3 plus 8x4 plus 5x6 equals to 0. So x1 plus 3x2 plus 8x4 plus 5x6 equals to 0. Then we have our second equation, x2 minus 2x3 minus 5x4 minus 7x6 equals to 0. Let's see where that is. So x2 minus 2x3 minus 5x4 minus 7x6 equals to 0. So you write that one. And finally, we have x5 plus 4x6 equals to 0. So x5 plus 4x6 equals to 0. Now we saw x3, x4, and x6 are our free variables. So we can put parameters for those. And then these are the leading or basing variables, x1, x2, and x1, x2, and x5. So I called x6 to be t, x4 to be s, and x3 to be k. And from equation 3, we know that x5 will be negative 4t because it's negative 4x6. From equation 2, isolate x2 and substitute those. You get 5k plus 5s plus 7t. And from equation 1, you can just get that negative 3k plus 8s plus 5t. And again, isolate x1 and then substitute the parameters for x3, x4, and x6. Now you can write x1, x2, x3, x4, x6 equals to, and then put those equations for each one more time. This was x3, x4, and x6. These were the free variables, and these are the parameters. Then you can separate them. But this is pretty long, but it's pretty easy to do it. So first you start with k's. So take all the k's. We have a k, 3k here, 2k here, k here, and the rest, if you don't have a k, put zeros. Plus, then you go with s's, negative 8s. And the second one, we have 5s. And no s here because it's a k. Then you put s and no s's there, so you put 0, 0. And for t, so let's look at it. 5t, then we have 7t, then no t's here, so you put zeros. and you have a negative 4t and a t, so you substitute those and you factor out. So now the span of the null space is going to be the span of these three vectors or any linear combination of those vectors. So that's a basis for the null space. And we had three variables. As I mentioned before, the dimension of the null space, which is the nullity of the matrix, is 3. So even if you don't do that, you can just get that number right away by looking at the free variables here. So 1, 2, and 3. So the nullity of this matrix is 3. Now the transpose of the same matrix, so that's what we have. So the transpose is 6 by 4. The RREF of the transpose is also 6 by 4. So you can write that. And if you want to find the null space of the transpose, so you can just the same way go to the RREF. Why, when I called those y, I didn't want to call them x's. So it's y1 plus y3 equals to 0 plus 2y3 equals to 0, and then y2 minus 3y3 equals to 0, and y4 equals to 0 from here. And you can go ahead and solve that. So how many free variables do you only have one free variable. So the null space of the transpose has to be one dimensional. So the free variable is y3. You can substitute, get y2 from the first one, y1 from the first one, and y2 from the second one. And then if you write y1, y2, y3, y4, you have negative 2t, 3t, and we called y3 to be the free variable. And I can say y3 equals to t here. And just factor out t, and that's what you get. So that's the basis for the null space of the transpose, and that's in R4. So please notice those, it's important. So we only have one vector, so it's one dimensional. Now let's go over the rank and the nullity of a matrix. Remember, the rank of a matrix is the dimension of the row space, which is the same as the dimension of the call space, and that will be the same as the rank of the A transpose. Again, the dimension is number of vectors in the basis. So in the, for example, the rank of our matrix, here we can just pick one of them. In the example that we did, if we go to the row space, we have 1, 2, 3 vectors. So the rank of this matrix is 3. If you go to the call space, you again see you have 1, 2, 3 vectors. So the rank of that matrix, again, is the same as the dimension of the row space and the call space. They're going to be the same. And we do see that we have 3 vectors in each one of them. Nullity of A, I'm going to repeat that again, is the dimension of the null space or the number of the free variables in RREF or the number of vectors in the basis of the null space. The nullity of A is the nullity of the A transpose is the dimension of the null space of the A transpose. Now know these formulas. If we have an n by n matrix, the rank of A plus the nullity of A is going to give us n right here. The rank of A transpose plus the nullity of A transpose is going to give us m. And an n by n matrix is full rank. Remember that word, and we are going to see that in the next lectures or next videos. So the matrix is full rank if the rank of A is the minimum of m number of rows or n number of columns. So in some problems you might be given one of those and they're going to ask you find the rest, which is pretty easy. Just substitute and find the you can find the rest. I think that's good enough for this video, and again please watch it 2-3 times and try some problems on your own. Thank you for watching everyone, and I will see you in my next videos. Have a good one.